Hi students, in this theorem we will discuss about the force between the two parallel current carrying wires. So I have just shown you in front of you there are two current carrying conductors. One is called as a B and A, and current is passing through it is called as a IB and IA. I have shown the direction of a force that we have to count it out, and this arrow is indicating what that after this theorem we will understand that what this arrow is indicating us. I want to just find it out that amount of force exerted by such a small segment of L, and both the wires are separated by the some distance small d. So first of all, that what this arrow is indicating, that I am just showing you two current carrying wires. Let's say this is the current and this is also current. Both these currents are in the same direction. So as per my thumb rule, I am just indicating you that this is the direction of my magnetic field, and this is also my direction of magnetic field. So you can see that direction of both magnetic fields are different, so both are having attractive force applying on each other. So this arrow is indicating that when current is passing in the same direction, both are producing that same amount of force, and that force is called as attractive force. So this is the theorem which we are right now discussing. So first of all, we have this theorem. We are putting that it's an initial expression. So you are aware about that expression, that first of all I am just putting in terms of magnetic field produced by that our current carrying wire A. You can take B as well, that is called as a mu 0 I of A, and then that is called as a 2 pi, and that is called as a D. You can say that I have proved this expression with the help of Ampere's circuital law. So I'm just putting that it is called as because of the Ampere circuital law, and I'm just naming it as equation number 1. Now I'm just proving another portion. You are aware about this formula, that is called as F is equals to Q multiply by that is called as a VD cross B, that is called as a cross product. I am putting that as sine theta. So I'm just putting that Q VDB sine theta, and that theta is called as a pi by 2 because it is perpendicular, so my angle would be pi by 2. So my formula will right now will become uh, F equals to Q VD and B. So you are aware in chapter number 3, whenever such type of number of charges are passing through such type of current carrying conductor, we are putting that if n number of electrons or charges passing from that conductor of area A and length L. So my formula, I am just multiplying this formula with Q VD B, n number of charges from A area and L length I have. So what I am doing is that these are the formula, and in a chapter number third one you are aware about that my current is also passing, that is called as a current density. It is called as A VD and E. Yes, you can just say that Q is called as a charge. So my equation contains now VD, then this is electron, this is area and length, and that is called as a number. So my equation is called as a B is left, current is left, and my length is left. So F equals to BIL. I have just taken that length my is capital L, so I am just putting F is equals to BIL. But here it is applying force because of that magnetic field on the first one, current on the second one, and length is L. So I am just putting that equation number second one. Equation number one's value is placed in equation number second. So we have equation number 1 available to us, that is the formula which I am just saying you that. So my equation of F, and then my equation number 1 is called as mu 0 IA divided by 2 pi d and IB into L. So I have just mentioned that values of equation number 1. So you can see that my formula will become for the force F is equals to mu 0 IAIBL divided by 2 pi d. So this is the equation of force experienced by our two current carrying wires when both are placed at some distance d. If you are just saying that my um, length is L, okay, instead of D, if you are this saying that Y, which is called as a perpendicular distance, and instead of IA you can just say that I1 wire, instead of IB you can say that that is called as I2 wire. So you can just remember this formula as mu 0 I1 I2 and then L divide by 2 pi y. It is up to you whichever way you want to just recall it. It is also valid, it is also valid, but right now from this equation I want to just derive the definition of ampere. What is the meaning of a 1 ampere? So first of all, to derive that those values I am using some of the primitive data, and then we will just derive the definition of it. Let's say initially I am assuming that current is passing from the both the wires is called as a 1 ampere if my perpendicular distance D is 1 meter, and I am just assuming that length of wire is also 1 meter. By placing all these values in this expression, you are aware about the formula mu 0 is called as a 4 pi cross 10 to the power minus 7. All those units are in terms of SI. So by putting this value in this expression, I can get that a value of a force is F equals to 10 to 2 cross 10 to the power minus 7 newtons. So in some of the school, sometimes board is asking you that if current and ideal values of length and perpendicular distances are used, your force will be what? So you can directly say that the value of a force, or you can use this formula. But I want to just define you that what is the definition of our 1 ampere. So the definition is called as if in current carrying wire, if distance or perpendicular distance between the wires is 1 meter and the length of wire is also 1 meter, then force applied is a 2 cross 10 to the power minus 7 newton. Then and then you can say that 1 ampere current is passing through it. So this is the primary definition. If you are assuming that your perpendicular distance between the two cable is 1 meter, length is 1 meter, your force applied by the both the cable is 2 cross 10 to the power minus 7, then and then you can say that our current which is passing from this wire is called as a 1 ampere. So by using this much data, also in exams they are asking for the 2 marks. Now I want to utilize this formula and derive one of the important notation for the cases, and these are the very important cases, and I'm just naming it as a cases of parallel wires carrying current. So first of all, we will just discuss about such type of cases. So first of all, my case number 1, I am assuming that I have two current carrying wire, and now current is in the same direction, and as per previous theorem, instead of using IA and IB, I have utilized that current in the both the part is the same. So my current I have shown in the both this part is same. I am just assuming that distance between them is called as R, and I want to find it out magnetic field at this point. So this distance between them would be called as R by 2 R by 2. So I'm just putting that magnetic field at point P. So this is my first case. What formula I'm using is that B is equals to mu 0 I divided by 2 pi d, or you can say that it's a Ampere circuital formula. If you want to that 4 pi over here, so my value would be multiply by 2 4 pi d. So whichever formula you will be convenient, you can utilize this notation. So first of all, I am using magnetic field for the first wire. So my formula will be mu 0 I divided by 2 pi, perpendicular distance is R by 2, and the same course is true for B2, that is called as a mu 0 I 2 pi r by 2. So if you have learned that properties of electric field and magnetic field, I am just using that B of net is a sum of both these magnetic field, but our magnetic field for the first cable is rightward, that is why positive, while the magnetic field for the left one is negative because it is applying on the negative side. So my equation would be B of net is equals to B1 minus B2, but you can see that B1 and B2 contains the same thing, that is why my B of net will give me that value, that is called as a 0. So you can just remember that whenever two current carrying conductors both are separated by the same distance or at a midpoint and current value is equal, then its a net magnetic field at its center will be 0. Next course, that is called as instead of point P, I am putting a point Q over here. From this current carrying wire I, it is X distance away, and from this current carrying wire, that is called as the parallel distance or perpendicular distance is R. This is the point P. So I am just using that at point Q. So this is my task. I want to derive that magnetic field at this point. So formula will be ready available to me. B is equals to mu 0 I. For my simplicity, I have mentioned that I1 and I2 both are equal, and that is called as a 2 pi. First of all, I am using B1, that is why my distance is R plus X. So 2 pi R plus X, and I am just using that another part B2, that is called as again current value is same, and the distance from the second wire is called as X. So my B of net will give me that both the magnetic fields are going on a rightward side, that is why positive. So this would be B1 plus B2. So my B of net is called as a mu 0 I and divided by 2 pi R plus X plus mu 0 I upon 2 pi X. You can simplify this one because concept is okay, but to remember this formula you require such type of short forms. So 1 upon R plus X upon 1 upon X. So this is the B of net, and that is called as on the right hand side at that point Q. Now case number third one, let's say I have both current carrying wires. My direction of current will be same, but my point is somewhere over here, which is not equally distributed. My distance between the 2 points, let's say this is R distance, and from this point, my from current carrying conductor, this distance is X, and from this one it is called as R minus X. So it is simple for you. Now I am just giving you a task at point P. So now you are quite familiar with this formula. First of all, B1 it is called as a mu 0 I divided by 2 pi, distance is X, and for the B2 that is called as a mu 0 I divided by 2 pi, and that would be R minus X. So this is the distance you have, R minus X. But you know that this for the first wire it is rightward side, that is why positive, and this one is from negative side. So my formula of B of net is giving me B1 plus B2, but actually that is called as a negative sign. So I can have B of net B1 minus B2. Thus my value of B of net is called as I am just bringing it out, all those things common directly. So mu 0 I divided by 2 pi is common, 1 upon X minus 1 upon R minus X. So this is the equation of your net magnetic field. So such type of three cases I have just shown you. When your current is in the same direction, in case number one, when current is in the same direction and that magnetic field at the midpoint, and then your currents in the same direction but your magnetic field at outside point Q, and thus I have just mentioned that not equal point, but it would be asymmetric distance you have, and currents are in the same direction. Now exclusive case I am just putting in front of you, when my both current carrying wires are separated by the same distances but their direction of the currents are different. So you can just see that figure. My currents are in the opposite direction, and my point P, let's say I'm just mentioning you that distance between both the cables are perpendicular, distance is same, that is called as r by 2, and this one is also r by 2. You can say that b is 0, but actually it is completely wrong, because in a previous case, likewise in the first case, we have dealt that the current is in the same direction, but right now I have mentioned that both the currents are in opposite direction. That is why a statement of a magnetic field will be 0 is completely false. So what we have to just do is that we have to first of all derive that magnetic field. So I'm just putting that net magnetic fields formula. First of all, you are familiar with the mu 0 I upon a 2 pi r or 2 pi d, or whichever distance you have taken. So for that I am just using Ampere circuital law b1, that is called as a mu 0 I is okay, then distance that would be r by 2. So you can say that mu 0 into 2I divided by 2 pi r. This is my first expression. Course for the second one, that will also give me the same value, mu 0 2I upon 2 pi r. You can just cancel it out, 2 and 2, that is okay for you. But what I want to just find it out, that is called as a b of net. That b1 is going on the right hand side, so b1 is on the right hand side, while your b2 is in opposite direction. So I can just say that b1 minus sign for the negative direction, because of the magnetic field is inside, it is on leftward side. So conventional sign convention we are using is that right hand side is positive and left hand side is negative. So I am also following the same notation. B1 is right hand side, that is why positive, B2 is left hand side, that is why negative. But you can see the direction of current is in opposite direction, so I am putting another negative sign for the direction of a magnetic field because of this current and at this point. So my equation will now become B of net is the summation of both the magnetic fields. So my equation B of net will be twice times mu 0 I, 2I, and divided by 2 pi r. So you can just say that that is merely the value, that is called as a twice times of a mu 0 I. So you can just say that 4 times mu 0 I divided by 2 pi r, and conventionally we are habitual to cancel out 2 and 2 two times. So I can just get that even such type of value, b of net equals to 2 times mu 0 I divided by pi r. So variety of examples I have placed in front of you. Very first one we have discussed about that current carrying two parallel wires, that theorem. After that we have just discussed about four different type of cases when your currents are passing like that. So theorem was only about circuitry, that is about Ampere circuital law, that original expression, and from that amount of force, and we have discussed about Ampere circuital laws formula, and from that 1 ampere definition in different type of cases. So I have placed almost all different type of cases in front of you, they related with our force between the two parallel current carrying conductors. So do revise for frequently, and you might be capable enough to solve some of the complicated examples. So these are the things you can just discuss about. One more thing I want to mention in the last case is that you can say that I have just mentioned b1 and b2, but this b of net will be at this point, so both are in the same direction. So you can just put such type of points at point b of net, and you can just say at a point q you can have a b of net, such type of points. These are the only meager amount of attention needed, but do such type of practice frequently, so you can capable enough to solve so many complicated examples of a NEET. Thank you.